Welcome back, math friends. This is AP Calculus section 1.6 day 2. We've already talked about exponential functions, and yesterday we were talking about inverse functions. So today it makes sense that we talk about logarithmic functions because the relationship between exponential functions and logarithmic functions is that they are inverses of each other. So let's take a look at this working definition that we have here for logarithmic functions. It says if a is greater than 0, the base, and a is not equal to 1, then the exponential function f of x equals a to the x is either increasing or decreasing. Remember, if a is a number between 0 and 1, it would be decreasing. If a is a number bigger than 1, it would be increasing. And this exponential function is 1-to-1 by the horizontal line test. If you picture exponential growth or exponential decay, hopefully you can see just by picturing that in your mind that both of those functions would pass a horizontal line test. Therefore, since exponential functions are 1-to-1, it must have an inverse function, f inverse, which is called the logarithmic function with base a and is denoted by that log base a. So here in this box, we have this relationship between exponential functions and logarithmic functions. I refer to this as changing form, but basically this is the definition of a logarithm. That if you have log base a of x is equal to y, then x should be equal to a to the y power, right? Basically this is just changing form between log form and exponential form. This is something that we've been doing in mathematics for years. Now if you think about exponential functions, parent functions, our domain is all reals, and our range is values that are greater than 0. Well, since exponential functions and logarithmic functions are inverses of each other, that means that the domain and the range switch. So for log functions, then, our domain is going to be x values greater than 0, and our range is going to become all reals. And of course, since exponential functions and logarithmic functions are inverses of each other, that means that they should be reflections of each other over the line y equals x. Our first examples are just a little bit of a review of logs, working with logs, and simplifying logarithmic expressions. These are brain power problems. These are not calculator problems. Letter A says log base 2 of 1/8. What does that simplify to? So if I think about this in exponential form, this is basically asking me 2 to what power is equal to 1/8. Well, hopefully if you think about it that way, it becomes easier because we know that numbers to powers become fractions when the exponent or the power is negative. So 2 to what power is 8? That is 3. That means that our exponent here, or what this expression is equal to, would have to be -3 because 2 to the -3 power equals 1/8. In letter B, we have log base 10 of the square root of 10. So again, I am going to change power, or I'm going to change form here, sorry. So basically, if I want to know what this expression would be equal to, I would say, well, 10 to what power is equal to the square root of 10? Well, what power gives us a square root? That is a 1/2 power, right? 10 to the 1/2 power is the square root of 10. So that tells us that this expression has to be equal to 1/2. And then our third expression, log base 3 of 27, that's asking us 3 to what power is 27? Well, hopefully you're realizing 3 to the first is 3, 3 squared is 9, and 3 cubed is 27. So this expression is equal to 3. We did all of those without the use of a calculator. The next thing we're going to review is our laws of logarithms, and you should remember these as well. If x and y are positive numbers, then log base a of x times y, multiplication inside of a log, is equal to log base a of x plus log base a of y. Multiplication inside of a log expands to addition of two logs with the same base. Law number 2, log base a of x divided by y, so we have a quotient inside of our log, is equal to log base a of x minus log base a of y. Again, this is our quotient rule of logs. Division inside of a log expands to subtraction of two logs with the same base. And then finally, log base a of x to the r power, okay, this is the power property of logs, says that we can bring that power r in front of the log where r is any real number, and it becomes a multiplier in front of the log. Example 2, A, B, and C are asking us to use the laws of logarithms to simplify or to condense the following expressions. Whenever they're asking us to condense, when we are done, we should have one log in our answer. That's what it means to condense completely. So when I look at example A, I have log base 2, log base 2, log base 2. So all of my logs are log base 2. So I am going to do this in a couple of steps. I'm going to start with the two logs that are positive. Okay, log base 2 and log base 2 of 6 and log base 2 of 20, those are both positive logs in this situation. So it might help to rewrite this as log base 2 of 6 plus log base 2 of 20, and then put the minus log base 2 of 15 at the end. And then these two, I'm going to use law number 1, which is that addition condenses to multiplication. So this would be log base 2 of 6 times 20 minus log base 2 of 15. And now I'm going to use the second law, which says that subtraction condenses to division. So this is going to become log base 2 of 6, whoops, sorry, added a 1 there. 6 times 20 divided by 15. And then I can simplify this. 6 times 20 is 120. And 120 divided by 15 is 8. So this becomes log base 2 of 8. And really, if we change form here, this is asking us 2 to what power gives us 8, which we know is 2 cubed, or 3. So completely condensed, this expression actually wasn't a log at all. It simplified to a whole number. The answer was 3. Let's take a look at letter B. In letter B, we have natural log of 5 plus 5 times natural log of 3. Well, first of all, remember that natural logs all have the same base, and that base is e. We don't have to write it, we just have to recognize that it is there. So the first thing I'm going to do on this problem is I'm going to bring that exponent that's now in front of the log back on the 3. So I'm going to write this as natural log 5 plus natural log 3 to the 5th power. And then, since I have addition right there, I'm going to condense these logs together into multiplication inside the log. So this will be natural log of 5 times 3 to the 5th power. And then I grab my calculator and I actually multiply 5 times 3 to the 5th power, which is 1,215. And then if I wanted an approximate answer, this would be an exact answer, natural log of 1,215. But if I wanted an approximate answer, now I could ask my calculator to compute that for me, and that is 7.102. And then finally, letter C. Again, it looks like we're adding and subtracting logs with the same base. In letter C, I just see the word log. I don't see a base written there. Please remember that when a base is not written and you have an log log, that the base is 10. That's the common logarithm, and so we shortcut it and we just don't write base of 10. But it is there, it's just invisible. So again, I am going to restore this exponent right here back on to the number inside the log. So I'm going to have log base 20, or sorry, log base 10 of 20 plus log base 10 of 2 minus log base 10 of 2 squared. And then I can do some simplifying. These two combine into multiplication inside the log. So I have log of 20 times 2 minus log, and I can rewrite 2 squared as 4. So this becomes log. Now when I condense again, 20 times 2 is 40 divided by 4. But 40 divided by 4 is 10. So I have log of 10. This is log base 10 of 10. So 10 to what power is 10? Well, 1, right? So this simplifies to a value of 1. When we work with logs, obviously it's nice to work with logs that have a base that is convenient for us because it's on our calculators. The two bases that our calculators use the most are log base 10 and log base e. And we like to work with base e, which has that special notation natural log x. So here in these 3 boxes are just a couple of relationships here. Log base e of x we write as ln x. If ln x equals y, then e to the y equals x. And natural log of e to any power is just going to be that power, or e to the natural log of x is just going to be x, right? That basically that this is kind of our inverse relationship here, that exponents and logs undo each other, provided that they have the same base, of course. Okay, so let's take a look at a couple of simplifying examples where we're going to use those definitions and the properties of natural logarithms to simplify these expressions. I'm going to do the same thing here that I was doing in my previous problems. I am going to look at this in exponential form. So ln, which is log base e of e, in exponential form is just asking us e to what power is e? And of course we know the answer is 1. In the second example, I'm looking at e, and then in the exponent I have natural log of 3x. Well, remember, natural log is log base e of 3x. So anytime the base of the log and the base of the exponent are the same, they just undo each other. So I am left with 3x for that expression. And then letter C is kind of the opposite of that. ln, again, is log base e. So if I have log base e of e to the x squared power, the base of my log and the base of my exponent are the same. They undo each other. So this expression simplifies to x squared. Recall that when you're working with logs, if you have to find the value of a log other than the common logarithm, which is base 10, or natural logarithm, which is base e, we can use our change of base formula to compute the answer. And we actually had an example of that in a previous set of notes where we used the change of base to compute an answer. Okay, so here I just have a little kind of a derivation for you of why the change of base formula works for figuring out what a value is when we have a base other than 10 or e. If we begin with an expression like log base 2 of 5 equals x, and we rewrite that in exponent form, then that would be 2 to the x power equals 5. If we take the natural log of both sides of the equation, we would have natural log of 2 to the x power equals natural log of 5. Then we can use the exponent property and bring that exponent on the 2, which is x, in front of the ln 2. And then finally, we can solve for x by dividing by natural log 2. So that's how the change of base works. All right, let's do a little bit of graphing. It says that when we are graphing logarithms, recall that it's often easier to rewrite the function as an exponent rather than a log and plugging y values in to find the corresponding x values. Okay, so before I begin, I'm going to draw a coordinate plane, and I'm going to be graphing all of these on the same coordinate plane. And I know that the domain of logs is x values greater than 0, so that's why I'm not putting much on the left-hand side of my y-axis here, because I'm not going to need it. Okay, so here's my coordinate plane. Let's take a look at letter A. Letter A, I have y equals log base 5 of x. Oh, sorry, there's a very, very tiny dot in front of that 5. That is log base 0.5. So really, this is y equals log base 1/2 of x. Sorry, that's very hard to read. So if I change this to exponent form, this is going to be 1/2 to the y power equals x. So this is what I was talking about above when I said it's easier to plug y values in and find corresponding x values. So for example, let's say I let y be 2. 1/2 squared is 1/4, right? So when y is 2, x is 1/4. That's going to be a point right there. When y is 1, 1/2 to the first power is 1/2, so that's going to give me a point there. When y is 0, 1/2 to the 0 power is 1. When y is negative 1, 1/2 to the negative 1 is 2. And when y is negative 2, 1/2 to the negative 2 power is 4. So notice that my base was a number, my base of my log, which was 1/2, was a number less than 1. And my log function is decreasing from left to right. Now in example B, we're going to be graphing a function with a base that is greater than 1. This is log base 5 of x. So if I rewrite this in exponent form, it's going to be 5 to the y power equals x. So now when I start plugging in my y values, when y is 2, five squared is going to be 25, which is going to be way out in the distance. Somewhere way out here. So our x value is going to be 25 when y is 2. When y is 1, 5 to the first power is 5. So that point's going to be right there. When y is 0, 5 to the 0 power is 1. When y is negative 1, 5 to the negative 1 power is 1/5. And then 5 to the negative 2 power is negative 1/25. So we're getting really close to that axis there. All right, so this graph, this is y equals log base 5 of x. Sorry, I should have labeled the other one. Y equals log base 1/2 of x. All right, moving on to letter C. Letter C, I don't see a base, so then I know it must be 10. So if I rewrite this, this would be 10 to the y power equals x. So again, I'm doing the same thing, right? I'm just going to be plugging in numbers. So when y is 2, 10 squared is 100. So that's going to be some very large number out there somewhere. Way out here. When y is 1, 10 to the first power is 10. It's right there. When y is 0, 10 to the 0 power is 1. When y is negative 1, 10 to the negative 1 power is 1/10. And 10 to the negative 2 power would be 1/100th. Okay. And then our last example, we have a base of e. So this would be e to the y equals x. So this time we have a base of e, okay? And remember, e as a value is like 2.71, okay? So if you don't know these numbers, that's fine. It's not a big deal. You can certainly find them on your calculator, but natural log of x is just going to be, it's going to pass, it's going to have that point at 1, 0, just like all the other graphs do, and it's just going to be a little bit higher here. Okay, so this is y equals ln x. So for the sake of time, we're just going to do that, but trust me on my points, okay, that's where that graph is going to lie. So what is the big takeaway from this graphing experience that we just had here? Well, the odd one out seems to be the log base 1/2 of x, because the other 3 log functions, log base 5, log base e, log base 10, all had bases that were greater than 1, but log base 1/2 has a base that's less than 1. So let's make a little notation here. If the base is 0 less than b less than 1, so b is some number between 0 and 1, we'll say the graph is reflected over the x-axis, or we could think of it as decreasing from left to right. And if our base is greater than 1, the graph is increasing, and the larger b, we'll say the slower the graph increases. Because if we look at our 3 graphs again, log base 10 of x, that was the biggest base we had because e is like 2.7, and then we had log base 5, and then we had log base 10. Notice that the green graph, y equals log base 10, that one is increasing at the slowest rate. Whereas the smallest base of those 3 was e, that graph is increasing at the faster rate. So the closer the base is to 1, the faster it's going to climb. And then the bigger the base is, the slower it's going to climb. Which hopefully, if you contemplate that, logs are the inverses of exponential functions. Remember, with exponential functions, the bigger the base, the faster it climbs. So we have that inverse relationship here with our base and how quickly our graph is climbing with our logarithmic functions. Our last examples have to do with solving logarithmic and exponential equations. So this is just a little review of algebra today. Let's begin with example A. We have e to the 7 minus 4x power is equal to 6. If we are trying to solve for x and x is up in the exponent, the easiest thing to do is to take, since our base is e, to take the natural log of both sides. So if I do that, I'm going to have the natural log of e to the 7 minus 4x power equals the natural log of 6. On the left-hand side, ln and e, log base e of e, cancels out. So I'm left with 7 minus 4x equals natural log 6. And then I just have to do the algebra to solve for x. So I am going to subtract natural log 6 to the left and add 4x to the right in the same step. So I'll have 7 minus natural log 6 equals 4x. And then I can go ahead and I can divide both sides by 4. So I get x equals 7 minus the natural log of 6 over 4. So this is an exact answer. If I want an approximate answer, I can then grab my calculator, making sure that I put parentheses around the numerator, 7 minus natural log 6, then divide that by 4. I get x is approximately equal to 1.032. So here is our answer for letter A. Letter B, I am beginning with a log. I have natural log of 3x minus 10 is equal to 2. So now the variable that we're trying to solve for is inside of a log. If I want to get that x out of the log, I need to change to exponential form. Okay. My base is e, so this is just going to become e squared equals 3x minus 10. And if I'm trying to solve for x, I would add 10. So e squared plus 10 equals 3x. I would divide by 3, and I get x is equal to e squared plus 10 divided by 3. Again, that's an exact answer. If you want an approximate answer, you can type that in your calculator, and you get x is approximately equal to 5.796. Our final example is the most fun. We always save the best for last. And in our final example, notice that what we have here, e to the 2x minus 3e to the x plus 2 equals 0, this looks like a trinomial. And what do we love to do with trinomials? Let's try to factor it. All right, so the first thing I'm going to do is I'm going to rewrite that e to the 2x. I'm going to pull apart that power of a power, and I'm going to write that as e to the x squared minus 3 times e to the x plus 2 equals 0. So now you can see I've got my variable term squared minus 3 times my variable term plus 2. So ignoring the e to the x for a second and just thinking about easy trinomial factoring, I'm looking for two numbers that multiply to make positive 2 and add to make negative 3. So hopefully you're thinking, well, that has to be negative 2 and negative 1, right? So I draw my two sets of parentheses, and I put negative 2 and negative 1 in the back. And then instead of x minus 2 and x minus 1, it's just e to the x minus 2 and e to the x minus 1. So the factoring is done. Now I use the zero product property to solve. So I say, well, e to the x minus 2 is equal to 0, and e to the x minus 1 is equal to 0. So this one gives me e to the x equals 2, and this one gives me e to the x equals 1. And I have to change, if I want to know what x is equal to, I have to change to log form. And since my base is e, it makes sense to change to natural log. So in this case, natural log of 2 will equal x, and in this case, natural log of 1 will equal x. Natural log of 2, that's an approximate number. So if we grab our calculator, a natural log of 2 is approximately 0.693. Natural log of 1, that is an exact value. that is x equals 0. Natural log of 1 is 0 because anything to the 0 power is 1, right? So if e to the 0 is 1, then natural log of 1 must equal 0.